I know that Nicholas will be wanting to see the recording.
All right, thank you everyone for coming. So as always, I will start by acknowledging the traditional custodians of the land on which EOW is situated. We pay our respects to the Aboriginal elders past and present, who are the knowledge holders and teachers. We acknowledge your continued spiritual and cultural connection to country. As we share knowledge, teaching, learning, and research within this university, we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. Today's speaker is Professor Allen Nutman, who's a longtime professor at UOW. I wanted to hype him up a little more, but he didn't give me. I asked him for a bio, but he just.
Like I said, I've worked here since 2010, and before that, worked in several other places. End of story.
So please welcome our man of mystery.
All right. Okay. So I guess I deal with a bit of a slice of time that most people here don't deal with. So I spent, I guess, a large amount of my working life in the Archean, particularly early Archean. Well, I do venture into sort of younger realms. So, for example, projects with Tim at the moment, looking at modern sediments, and also Alan Shivers, dare I say, doing zircon work on stuff which is just over 1 million years old from the Solomons. But my heart is mostly in early Earth history. So I'm going to look at recycling into the Eoarchean Earth. The Eoarchean is that slice of time that goes from 4,000 to 3,600 million years ago. Come on. Just got it. Good. So first of all, I'd just like to say thank you to my two main co-workers, Clark Friend. We've been working together since 1976, in other words, 46 years we've been working together. Vicky Bennett and ANU, we've been working together 33 years. This just sort of shows us contemplating Eoarchean marbles, nearly inland ice in Greenland. This is quite interesting because one sees very assertive things stated in the literature that when you go and look in the early geological record, there's no carbonate sedimentary rocks present. So we're a bit mystified why what's written in the literature doesn't agree with what we see in front of our eyes. Anyway, so what I'll be talking about today encapsulates a large amount of stuff which was in this paper, plus some new results, including some which emerged this morning and which needed some little rapid changing of the presentation, and also some future directions. So the Eoarchean Earth, 4,000 to 3,600 million years ago, you can't always take things for granted. So when you're working in the Phanerozoic, you can take plate tectonics for granted. Throughout probably a large amount of the Precambrian, particularly back throughout the Proterozoic, the vast majority of people will take some form of plate tectonics as a given. And when I mean plate tectonics here, it means that basically the lithosphere was laterally mobile, meaning that you had divergent zones and you also had convergent zones where some form of subduction-like process was taking place. When you start to get back into the earlier bits of the Archean, that isn't always a given. There are models around, and I say models because in my opinion there's very little evidence to back it up, that in fact when you go back to the start of the geological record in the Eoarchean, some people are suggesting that the lithosphere worked in a different fashion and was actually what was called a stagnant lid, dominated by vertical processes. So this little cartoon here, which I lifted from somebody's paper, shows sort of some of the scenarios. So basically you have this stagnant lid evolution, where basically you don't have significant lateral moving around of bits of the lithosphere on the surface of the Earth, but instead most of the evolution is vertical, and people see an evolution from an early magma ocean. Shortly, basically, probably the last magma ocean was the moon forming event. And then as that gradually through time, as that gradually cools off, you go through what's called a heat pipe process, where you actually have got residual bits of that magma ocean still venting onto the surface into vertical drips and plumes, and then which would be represented by what's regarded, for example, Venus, Mars. And then finally, you have a terminal stagnant lid, which would be somewhere like Moon and Mercury. On the other hand, Earth is obviously very different nowadays. And the question is, when did Earth diverge from that stagnant lid scenario? Was it actually very early in Earth's history, well back in the Hadean, or well back before 4,000 million years ago? Or was it after 4,000 million years ago, sometime in the Eoarchean? And the big difference, one big difference between these systems is that if you have a mobile lid, you've got a much more efficient mechanism to recycle material which has been at the surface into the deep Earth, even down to the core mantle boundary, as presently happens with subduction graveyards in the Phanerozoic. On the other hand, if you have this heat pipe drips and plumes system, is actually much less efficient at recycling sufficient material into the deep Earth. Well, people might think, well, who really cares about that, really? But it actually has quite significant effects on the Earth. So, for example, if you have a wet mantle, the viscosity of that wet mantle is significantly different from the viscosity of a dry mantle, and that will obviously have very significant effects on convection regimes. So what is the evidence, at least in the Phanerozoic, that the, should we say, the mantle is wet? Well, there's actually growing amounts of evidence. So, for example, if you look at modern bits of regurgitated subduction systems, for example, in the European Alps, basically what's happened is that stuff has gone down into the mantle in very deep in subduction zones, and then actually being regurgitated up and got caught within the alpine mountain belt. Then what's found is that nominally anhydrous minerals, NAMs, such as olivine, actually take in water at mantle pressures. And also you get various associated high pressure accessory minerals, such as the lovely mouthful titano-clinohumite and titanochondrodite. Those minerals are also water bearing. We'll be coming on to this later. So basically, this is an example of an FTIR mapping of alpine olivines. In some of this stuff regurgitated up from mantle depths from pressures of about 2.5 gigapascals, where the olivines have got a significant amount of water in them. When you get to greater depths, basically isochemical minerals such as ringwoodite also hold significant amounts of water. So actually, there's certainly models out there where people think that if you think of the whole of the Earth's water budget, that actually only about 25% of that water is out here in the hydrosphere and cryosphere, and actually about 75% of Earth's water is locked in the mantle in these various minerals, such as olivine, which is at these surface pressures is nominally an anhydrous mineral. In other phases like ringwoodite, which can actually contain up to 2% water in them. So as I said, why is the recycling of water and other superficial materials back into the deep earth important? Well, just one example is it affects viscosity and therefore convective regimes. Okay, so there's evidence growing for this in the Phanerozoic Earth. But what happens when you go and try and find evidence for this kind of stuff in the Eoarchean? Well, the first problem is, because of Earth is a restless place, all these billions of years of tectonic activity, that there's almost no Eoarchean rock surviving. So in fact, at the moment, only about 1/1,000,000th of the crust is probably Eoarchean. And the Nook region in Greenland is the best. It's about 3,000 kilometers squared there. So this stars here show places of known Eoarchean crust in the world. Some are very variable in quality and availability. Most of them, for example, Antarctica, South America, Southern Africa, Western Australia, they have only got meta-igneous rocks. There's actually no ancient sedimentary rocks that are preserved at all. Some of the other ones are rather difficult to access, so I don't think I'd want to go and look at the Eoarchean in Ukraine at the moment, or actually, of course, we'd be completely locked out of looking at it in Xinjiang. So but regardless of that, the Greenland stuff is best. It's got the most complete and comprehensive geological Eoarchean record. So this is the area that we're looking at, made from oblique Google Earth images. So basically, there's this tract which runs from the inland ice up at this place called Isua, up by the inland ice, and it runs through a fjord complex to Nuketown, and then through to the islands just south of that. So basically, that tract there is the best place to look at Eoarchean processes in the world, and of those, probably Isua is the best of them. Okay, so when you get to Isua, there's something called the Isua supercrustal belt, which is a belt, an arcuate belt about 35 kilometers long, consisting of metavolcanic and sedimentary rocks. So this was discovered in the late 1960s. There's a massive positive aeromagnetic anomaly by the inland ice, and this is due to magnetite-rich Iron Mountain there, where you've got over 1 billion tons of banded iron formation. So over the years, quite a few companies have looked at it, but of course, because of its location, it's very high cost to get the ore out of the ground and also get it back down to the coast so it can be shipped. So we're going to be looking at part of the Isua supercrustal belt. One bit of it has got sort of about 3.7 billion-year-old rocks, and then the other bit of it's actually 3.8, but it's a 3.7 billion-year-old bit that we're going to be looking at. So when it was first discovered in the late 1960s by a prospecting company, there was no idea how old it was. But in 1972-73, partnership between the New Zealander guy, Vic McGregor, who actually lived in Greenland, and the Oxford Isotope Group, they demonstrated the Archean age of Isua. So it's the first time I was ever in Isua, 1978. Not particularly auspicious arranging in the snow like that. Anyway, so why Isua? Well, when you look at this very old geological record, it's just been through the mill so many times, so many metamorphic events, so many deformation events, that it's very hard to find anything that, if you like, is still original. Okay, you might be able to date the rocks and show it's very old, but finding, for example, relic sedimentary structures, relic igneous structures is extremely rare because of the superimposed tectonic and metamorphic effects. However, I guess all natural processes are chaotic, and the example or analogy I like to take is this where a storm has gone through a residential area in the US, and just completely by fluke, you just got one or two buildings actually left standing. The same, of course, happens with bushfires here. You can just by complete fluke have an area completely wiped out and then just have one house left standing. So basically you get this random surviving, if you like, original structures, but these are only make a very tiny amount of the Isua rock. So there's a lot of hoofing it over the ground to find those few places where you can really get a lot of information. Another problem is basically there's huge swathes covered by moraine from the last ice retreat. This hides a lot of rock. So I'm putting in some of these pictures for some of you, what I like to call gardeners, just so that there's something of a little bit more interest for you to watch, okay? So basically, you've got these enormous swathes of moraine, which can actually hide a very large amount of the geology. So this shows a big moraine field running across the Isua area. Good walking ground, but the rocks are few and far between. So that big swathe of moraine goes over the 3,700 million year old part of the Isua belt that we're interested in. So this shows we're standing on the edge of the moraine, and then just beyond it, you've got all the outwash sands in the middle distance. That's the end of the geomorphology. So anyway, we're on this 3,700 million year old part of the Isua supercrustal belt, and there are these two starred localities, a little bit more superficial stuff. The lakes are very different color. The nice blue ones are just local meltwater river lakes. The horrible grey thing basically is being fed by meltwater from the inland ice and is all full of rock flour. So basically, those two starred localities there, these bodies of metaperiddotites, and we find them imbricated with metabasalts, bonanites, which in the Phanerozoic is a type of volcanic rock you only find in arc situations, particularly forearc situations, cherts, and also andesitic greywacke. So people who've worked on convergent plate boundaries will immediately recognize that as a sort of very plate boundary-like assemblage. And the map there of my geochronology shows you have all these strips of different lithologies, all imbricated in together, with slightly different ages, but all somewhere around about 3,700 million years old. And again, so those are localities that we're going to be looking at. So basically, we're going to be looking now just at the one in the distance, which I call lens B. And this basically shows a little bit more detail of the character. So there you have this big blob of ultramafic rock, peridotite. And when you actually look in the interior of that blob, you can find all these porphyritic olivine grains, which are lying completely oblique to the trend of a regional structure, which I show, with the dashed yellow line, versus the orientation of the olivine porphyroblasts within that peridotite. When you look at the margin of these bodies, they're all ultramafic schist with carbonate in. They're completely tectonic boundaries, and they're against rocks in this particular case with a geochemical signature of island arc foliites. So basically, again, not only does the appearance of the way the rocks map out basically hint at a convergent plate boundary but also when you actually look at the chemistry of a rocks, it's the same as well. So talking about the chemistry of a rock, what about their chemistry? Well, when you look at the major element chemistry, which are these diagrams bottom left, they actually, all these whole rock analyses of these particular peridotites sit on what's called the basically the depleted mantle line, which is that line running up diagonally sort of northwest across that diagram. So this shows that these rocks have actually got, in terms of their major element chemistry, they've got the characteristics of bits of depleted mantle. On the other hand, you can get other types of peridotites, which have got a different origin. And I'll ring some on here in red. So when you go and look at the map over there, one's got a serpentinized pickrite. That's a volcanic rock, which actually, before it was metamorphosed, it had a large amount of olivine in and was essentially verging on a peridotite. But there are very, very few surprisingly igneous zircons in it, where you get the age of about 3,720. But when you look at those sort of rocks, basically peridotites or verging on peridotites, which are formed by accumulation of crystals in a cooling magma, they actually have got a rather different composition. They plot on the right-hand side of the mantle array because they've got more aluminium in them. When you look at the trace elements, and again, focus on the black squares in the top left-hand diagram, you find that these peridotites from the lens A and B, they don't sit within what's called the mantle array, which involves things like morb and so on, and they sit up in the what's called the arc field, because they've actually had thorium added from the slab-like dehydration. So basically, when you look at the whole rock chemistry, they really start to have the signature of the bits of mantle that have somehow got trapped amongst all these imbricated bits of different volcanic and sedimentary rock. And the imbrication happened, something like 3,700 million years ago. Texturally and mineralogically, when you actually look at the two lenses, even though their actual chemistry is almost identical, they actually, texturally and mineralogically, they are very, very different. So when you look at this southern lens A, the olivine is FO9192. For those of you who are not sort of conversant with this mineralogy, that means it's a more iron-rich olivine. You get associated with it in between the olivines, you get little relics of chrome spinel, which I'll get on into a moment. And even within the olivine, you can find very small, rare inclusions of clinopyroxene within the olivines there. So on the other hand, when you start looking at lens B, that's the northern one, the actual textures of mineralogy is radically different. So in lens B, you have got porphyroblastic olivines. Basically, those are not igneous olivines in any sense. They've actually grown during a metamorphic event, and they are actually enclosing patches and trains of magnetite, even with sort of conjugate boundaries between different magnetite bands. And they also have included within them early antigerite. Antigerite is one of the serpentine varieties of mineral. Also, these olivines have got a much higher magnesium content. They're almost pure magnesium olivine, whereas the ones in lens B, they're actually a bit more iron-rich. Another thing you start to see is within lens B, you get these weird minerals in the olivine. basically this something called titanochondrite or titanoclinohumite, which I'll get into a little bit more in a moment. So when we start looking at lens A in more detail, and this is where we get back to the those rare spinel relics between the olivines, they have actually got a composition of the kind of olivines that type of spinels you'll find in oceanic suprasubduction zone peridotites. In other words, stuff which was trapped between an arc and the go down going subducting slab. When you look at lens B, this is where you also start to get something different, the so-called titanoclinohumite minerals. And this is on the, they are isostructural with olivine. So you've got an image there, an SEM image, 10 micron scale, where you've got these zones of these titanium bearing minerals just all intergrown with the olivine. So what you're actually seeing here is you're seeing olivine porphyroblasts in type B, overgrowing magnetite and replacing an antigerite bearing precursor. In other words, one's looking at metamorphism of serpentinite. So the rocks have been completely wetted, and then in a metamorphic event, they started to grow olivine and dry out a bit. So this is what I think the likely scenario for the difference between the two varieties. So we start off top left over there with a bit of mantle. That bit of mantle is an aggregate of mostly olivine and depleted mantle. You don't have much or any pyroxene left. It's largely olivine. You have small amounts of little bits of this chrome spinel. You've got a small amount of clinopyroxene present as well. And then depending on what happened to that domain of mantle in that wedge situation there on the right, if you had a situation where you had a more or less a rock dominated environment, a bit of water filtering in, then you end up with, of course, development of serpentine minerals as a network around relict igneous mantle olivines. On the other hand, if you have a so-called fluid-dominated system, what you end up with is a complete breakdown of the original mantle mineralogy dominated by olivine. You start off with a rock which is then dominated by serpentine minerals, and because serpentine isn't particularly keen on iron, you have all the magnetite in with the serpentine as well. And then what then happens during, and I'll get onto this later, ultra high pressure metamorphism, is that you start to grow these big porphyroblastic olivines in the fluid dominated rock, whereas in the rock dominated rock you just start to grow little new fringes of olivine around the relict mantle olivine in that rock. So this kind of scenario here also fits with what you actually see in the geology of Isola, in that you have got the associated crustal rocks, imbricated basalts, bonites, chirps, andesitic greywacke, just the kind of thing you'd expect to find, sort of fairly deep in a four-arc region of even in the Phanerozoic arc. So where does the metaserpentinite water come from? Okay, so this is on the left, work done by two people. One, Maria, who at the time was a PhD student in ANU. She did the actual oxygen isotope work on the olivines, and then Allen did the whole rock on the rocks to complement the olivine work. When you start looking at the oxygen isotopes, of the olivines in the two different variants. When you look in this lens A, where it looks like one's got relict mantle olivine still preserved, then in fact what you have, the oxygen isotope signature of those olivines matches mantle olivine, more or less, pretty good. When you go and look at the olivines in that variety, second variety, where all of the olivines were actually seen to have grown from metamorphism of the serpentinite, then in fact you get a different oxygen isotope signature. And basically the best way to explain that is the serpentinite was formed by basically you take an ultramafic rock and you circulate heated seawater through it. And then you end up with this shift in the oxygen isotope signature. So it looks like one's getting the first hints that basically the serpentinization was a surface-related process. You're getting communication between mantle-like materials and surface water. So when you look at the electron probe analyses of the olivines, the ones in the high FO 9696, in other words, the ones which had formed by metamorphism of the serpentinite, you get slightly lower totals than in the mantle-like one. So this is giving a hint that detectable water. And basically, when I wrote this in the week, I said water analyses of the olivine are in hand. And as it should so happen, they actually arrived this morning. So anyway, sort of fitted nicely. So this is by a guy called Eoarchean, Switzerland. Basically, he's been doing FTI analyses of the olivines, and he finds there's quite significant amounts of water within the olivines in the variety B. When he looks at the relic mantle olivines in lens A, he can't detect any water in the olivines. Not only that, but he points out that it's remarkable that in materials this so old, you're actually preserving a zonation of hydrogen diffusion in these minerals. So basically, he says that the hydrogen diffusion is related to growth of regrowth of olivine around the outside, giving the clearer olivine, which has got a lower water content, which of course suggests that the 60 ppm maximum that you can see in these is probably an underestimate of what was originally there. So that's the stuff which actually fortuitously came in this morning. Okay, so we can actually see now there's very robust evidence that in the Eoarchean there was communication between the hydrosphere and the mantle, giving water-bearing olivines, and these kind of things are going to have an effect on the, for example, the viscosity of the mantle. So let's look at some other things. The other thing which pointed out, you've got these weird accessory minerals called titanochondrodite and titanoklinohumite, and all of the geological observations plus experimental data indicates that when you have these kind of rocks in these kind of minerals in mantle compositions, they're only stable at extremely high pressure, with the boundary between the phase boundary between those minerals occurring somewhere above 2.5 gigapascals. In other words, that's at pressures much greater than are going to be realized in the crust. And again, it shows that this stuff has actually been down into the mantle and then regurgitated up as slivers within this probably sort of 4-arc assemblage. So basically, there's very good evidence that these rocks have suffered ultra-high pressure metamorphism, which again leads on to another debate or squabble, and that is you will find in the literature that when you go back into the early Archean, there isn't any high pressure metamorphism, but there obviously is. And so basically this diagram here on the left there is a compilation of Brown and Johnson of metamorphic conditions. What you have up there for the y-axis is the apparent geothermal gradient of metamorphism. So if you're down near the bottom of the diagram for the black, you've got very low geothermal gradient. In other words, if you go down into the earth, the temperature is only increasing gradually. If you go up to sort of 1500 degrees Celsius per gigapascal, those are much steeper geothermal gradients. So according to the literature compilation at those times, 2018, the last and extremely rare evidence of ultra-high pressure metamorphism, which is related to subduction-like processes, was about 1,800 million years ago. And now we've actually got evidence back at about 3,700 million years. So basically, these kind of metamorphic regimes are very, very hard to fit into a stagnant lid, okay? Where basically you just have a blanket crust being heated and maybe churned around a little from below. You in no way have got cold stuff diving back into the earth like you do in subduction systems. So again, the metamorphic side of things fits very well with actually a mobile lid, in other words, some form of plate tectonics rather than stagnant lid. And again, that kind of mobile lid is much better at mixing sufficient material into the deep earth than the stagnant lid. So I think that uniformitarian rules, at least back to about 4,000 million years ago. Okay, so one's actually learned quite a lot from these two little lumps of rock, but we might be able to learn some other things. So if we go back to those serpentinites, which are formed by alteration of this layered pickrite flow, 3,720 million years. Basically, collaborators did halogen geochemistry on the serpentines in them, and this sort of diagram here encapsulates sort of the storyline. Basically, average marine sediment is much enriched in iodine over chlorine because life prefers to sequester iodine over chlorine. Therefore, modern seawater has got actually a much lower iodine relative to chlorine content. So what they found is that when really the freshest of these serpentinites, which have been altered from seawater circulation, and this is known from the oxygen and hydrogen isotopes, basically you end up with a rather low iodine-chlorine ratio, less than you'd expect for mid-ocean ridge basalts and primitive mantle. And this is a signature maybe of biomass in the Eoarchean. So one thing I want to try with Mark Hendrick is to then take these lumps of mantle, which have got lots of serpentine in, and basically see if we can actually see this biosignature getting down into the mantle in the Eoarchean. And of course, you know, anybody who's got diamonds realizes that that biosignature does get down into the mantle. After all, you know, diamonds are basically formed from metamorphosed dead us, you know. So anyway, the other thing that we're going to try is someone looks at the sulfur isotopes of these. when you go back into the Archean, the atmosphere was a little bit different. And that is because there was no oxygen in the atmosphere, there was no ozone, there was much less shielding of the atmosphere from cosmic radiation. And this did weird things in sulfur isotopes, which one can only understand if you know quantum mechanics, so I won't go into it. But what it means is you get very weird fractionations of sulfur isotopes in the Archean atmosphere, which are unrelated to normal mass fractionation processes. So one thing that we hope to do in collaboration with Janina later is when you look at these serpentinites bearing with the growth of the new olivines, there's a bit of the high pressure titanium rich phase intergrowing with the olivine, you actually find rare sulfide grains within them. Some of them are pyrite and some of them are galena. And the idea is we want to see if you can have evidence of atmospheric communication with mantle rocks at that time. So the bottom right plot gives you the idea. You've got to, don't worry about what says on the X and Y axis. Basically, if you're 0 on that plot, you're looking at sulfur, which is interior Earth igneous sulfur. If you're somewhere up in the northeast quadrant at this atmospheric S0, that's a particular isotopic signature of atmospheric sulfur at that particular time. So other people have looked at the sulfur isotopes of isoabanded iron formation, and they find that it occurs on the mixing line between interior Earth volcanic sulfur and atmospheric sulfur. So that's a very nice story. We would hope that when work on these particular sulfides, tiny sulfides, you can see that's about 20 microns across. Within these peridotite, then we'll hopefully get something lying on that line there, which I've done with the big question marks. We're finding when you actually really start looking at geologically well curated history samples, that you're getting a diversity of these sulfur mass independent fractionation signatures at 3,700 million years. And most importantly, and this is stuff that we're writing up at the moment, these rare stromatolites that we found at just simply one locality, within them, there are extremely rare small pyrite grains. And basically the pyrite grains are not the shape that you expect to see. They obviously look like, from their habit, like they were actually replacement of some other mineral. And then when you look at the signatures of these pyrites out of the early stromatolites, they've actually got a signature of reduction of Archean seawater sulfate. Very, very different from what you can see in the banded iron formation, which stratigraphically is actually very close to these units which have got the stromatolites in. And then when you look at that middle plot there, it seems that the smear of the data is what you'd expect the sulfate reducers. So we think we've actually now got the most ancient metabolic pathway documented with basically reduction of seawater sulfate with active 3,700 million years ago. So the sulfur isotopes are another avenue to pursue. So talking about sulfur isotopes, basically there have been hints of communication between the atmosphere and fairly deep conditions from this work which was done on Archean TTGs. That's tonalites. Tonalites are the main rock in the Archean. But basically showing that from the sulfur isotopes that there was a communication between the atmosphere and the deep environment where the melting was taking place in order to make these particular type of igneous rocks. So what about this gap in the high pressure metamorphic record? Well, it's often the case that when you people start finding things, then people go back and look, and they can actually find more examples of it. So we've got this gap of from about 1,800 million years back to 3,700 million years. So can we find more evidence of this ultra high pressure metamorphic record, which clearly links into subduction systems, recycling of surface material into the deep earth? Well, there's actually already cryptic evidence out there, even if you don't actually have locked in the crust remnants of ultra high pressure metamorphism. First of all, is if you look at kimberlites, those are the diamond bearing things which bring up chunks of the lithospheric mantle with them. When you look at the Eoarchean eclogites, high pressure metamorphic rocks which are brought up from mantle depths, basically those eclogites are the kind of source materials to make most Eoarchean crust. They also would have equilibrated at these very low geothermal gradients. And then also experimental data shows that generally the preconditions for making any of these sort of Eoarchean tonalite nice compositions, you do need to have a very low geothermal gradient. So there is increasing lines of evidence to show that you've got a whole range of evidence of plate tectonics of some form taking place back to the start of the rock record, which is about 4,000 million years ago, recycling surficial material into the deep earth. So looking at this gap is actually being redressed by some current GeoQuEST funding, and looking at some younger Eoarchean metaperidotites in the Nook region. Well, in the days of my youth, one came across sort of metaperidotites like this, and one just simply thought, oh, they're a terrible mess. We can't do anything with these. See my 1976 notebook on the picture there. So basically, what we now realize is these messy ultramafic rocks like this, they're now actually metaserpentinites that grew porphyritic olivine, and we've got to establish under what sort of pressures some of these occurred. And one example on the right here, which is at the moment only on the base of fin section optical work, there isn't any SEM work yet, this is a late Eoarchean metaperidotite, and the olivine has got inclusions of titanochondrite or titanophenohumite. So I suspect that the more, when other people start looking at these ancient peridotites, there's going to turn up more evidence of high pressure metamorphism. So in summary, the earliest geological record provides an increasing range of evidence of some form of mobile lid plate tectonics, otherwise known as basically plate tectonics, mobile lid. This focus has been on fragments of the mantle lightly trapped in the crust, but it has previously been affected by communication with surface fluids, recycling surficial material deep down into the earth. So that's it for now. Thank you.
Thank you, Alan. Does anyone have any questions?
Yeah.
Yes.
Actually, the modern context of, I suppose, continental rock versus ocean
Yeah.
material, and the continental rocks all rise over the ocean.
Yeah.
Term, subduction zones.
Yeah.
That implies a fair bit of fractionation of rocks over quite considerable time. So, at sort of like 3,700 million years ago, is that, or 3.7 billion years ago, is that stuff that's preceded,
yeah. So basically, what you have is you don't actually have any relics of oceanic crust. Just like in the Phanerozoic Earth, basically it's only extremely rare instances that you actually have any relics of true oceanic crust trapped in the continental crust. Most of it just goes down subduction zones. Some of it gets trapped sort of halfway down the mantle, but the seismics show that actually a lot of it actually gets back down to the core mantle boundary to form what some Japanese colleague of mine called the anticrust. Down there. When you actually look at the most ancient geological record, it is actually just as diverse as the modern one. Of course, there's some subtle differences because the atmosphere is oxygen free. You're not going to get any, for example, red bed sediments because the atmosphere wasn't oxidizing the surface. I hope that answered the question.
Thank you.
Okay.
Yeah. Follow on from that. So you said you found more than part of in these lenses. Is that formed as part of the subduction, or is that like the equivalent of an ophiolite?
Basically, when you look at the chemistry of the associated basalts, all those green squares and circles, they are sort of foliatic, like a lot of more, or majority of more basalt is. However, they've got a distinctly different chemical signature, and that's why they're known as actually island arc foliites. So actually, again, you get very little, if any, more preserved in the early Eoarchean. I think that it's just simply went down subduction zones, because after all, you can't find on the surface of the Earth. The oldest morb on the surface of the Earth is in the Northwest Pacific, and it's only about 200 million years old. Yeah. So basically, if you like, all of the primary crust tends to get recycled back into the Earth, and shall we say, what one's seeing when these sort of arc complexes is, if you like, the start of some secondary crust, which is developing at those convergent plate boundaries.
I actually have a question.
Yeah.
Since I'm not a structural geologist.
Yeah.
Near the beginning, you were talking about these imbricated,
Yeah.
I guess, minerals. I'm just wondering how those form. Is it just from sequential faulting?
Yeah, it's just basically slicing. It's literally slicing and sort of stuff together. So when you look on this diagram here, which is my mapping, you can see that you've got all these different colors of little slices, and a lot of them they've got red boundaries to indicate they are actually all tectonic boundaries. They're early tectonic boundaries because we actually have sets of dikes which cut across. The dikes are with tonalite and so on, about 3,700 million years. So in other words, that basically this interleaving and so on is extremely ancient. Is that
yeah?
all right?
Thank you. Any other questions?
So just for more biological types, this sort of iodine chlorine thing might actually provide a very interesting and bit freaky way of trying to actually get some idea of biomass throughout the whole of the geological record. because you're recording basically what the seawater was at the time. So it might be something interesting for somebody to pursue, probably when I'm pushing up daisies. All right. Any other questions?
I have slightly tangential one.
Yeah.
Over the course of 4 billion years or whatever, is there a flux of water between the mantle and the surface? And if so, what ways?
Well, again, that's an interesting question, and people are trying to obviously establish whether there's been a more or less, should we say, equilibrium. As I say, some estimates say 75% of the water's down there, 25%'s up here. But there's definitely a very fashionable topic at the moment. And of course, it's amazing we got just the right amount of water on this planet. Do you know why? Because if there was a bit more water, all the continents would have been drowned throughout geological time, and people like us couldn't have developed. Because, okay, shall we say, dolphins are highly intelligent, but they definitely took a very different, shall we say, route from us. You need dry land in order to develop all this kind of stuff that we use.
So you're saying we might have been a planet of dolphins?
Yes.
Just following up on that, I don't really interesting to hear about the 75-25.
Yeah.
How robust is that?
It's not robust, but people realize it used to be thought, once you get down into the mantle, everything is pretty dry. But people are realizing more and more there is a significant amount of water down there. And the question is, okay, people are going to be arguing about the ratio, but overall, people now will agree there's a significant amount of water down in the solid earth.
Just a follow-up from that.
Yeah.
Because I thought water isn't really stable down there, because from what I learned during subduction, most of the water is sort of released.
Most of the water is released, but when you subduct something, there's an enormous amount of water. Basically, if you imagine a crust with all the pillar lavas and so on, you've got all the sort of water between the pillows and so on. Okay, a large amount of that does escape. But when we're talking about water in the mantle, it is not, shall we say, as free H2O. What it is OH coordinated in minerals down there. And you're not sort of talking about actual free water down there.
Right. Right. If there's no more questions, thank you, Alan, again.
Okay, all right. You're welcome.
And yeah, please enjoy the pizza and beer.
So I hope the meringues chewed you up.
Yeah, they did.
Late, isn't it?